Okay, we are going to study binary logic. We've been doing a lot of that. Computers are binary, as we know. It's either on or off, true or false. So this is going to be true and false. We are going to study simple and then more complex connectors. So basically, we need to think about a statement like, it is July. Just a statement. It's a true statement. And here's another one. It snowed today. Well, that's not true. It could become true later. It doesn't matter if it's true or false, but it's a statement, and we will give these statements a label P and Q. And then we'll make complex statements. It is July, and it snowed today. Well, is that true or false? That would be false because this part is not true. We could also connect it with or. It is July or it snowed today. Well, it's July. It didn't snow today, but it has or, so this is true. So the whole statement together is true. It is July or it is not July and it snowed today. So what we're really doing is we are connecting statements and we are deciding if they are true or false, because binary logic says it's either one or the other, true, false, on, off. So we're not going to actually use the statements. We are just going to say we have any statements. One is P, one is Q. Now we need to, there are 4 possibilities when you have 2 different statements. And so P, we're going to say true, true, false, false. And we will always list in this way, in this order, just so that we know our answers at the end are the same. And then this will always be alternating, true, false, true, false. And what we're going to do then is we're going to connect it. So we have some basic connectors. This is an AND connector. And for an AND connector, like with the statements, both must be true to be true. And this is an OR connector. At least one must be true. To be true. To be a completely true statement. And this little wiggly guy is a not or a negation. And it basically negates the original. So if I say it snowed, it did not snow. If I say it is July, it is not July. Crazy that those lines are like that. So anyways, you always start with true, true, false, false, and this is alternating true, false, true, false. And there's always 4 when you have 2. Essentially, 2 to the power of 2 equals 4. We'll get to where we get longer ones. So first, let's do a P or Q. So now keep in mind that that's an or, and at least one must be true to be true. So if this is true or this is true, it's true, the compound statement. This one is true, so it's true, false or true, so true, and then false and false would be a false. So here's my result. Now let's do another one, PQ. And we're going to go P and Q this time. Remember, they could be any statements. If the P statement is true, true, false, false, what do we get? An alternating true, false, true, false, always starting that same way. So if this is true and this is true, then it's true. Remember, that's an and both must be true. If this is true and this is false, well, then it's false. False and true is false. False and false is false. So there's only two possibilities, true or false. That is our binary logic. A little side note here. So we're just going to use P. So if there's just P, it's either true or it's false. We don't need for. And then not P, that's our negate. If it was true, now it's not, it would be false. If it was false and now it's not P, it would be true. So it just turns it into the opposite. So now we get a few more compound connectors. So our compound connectors are like so. Can't spell today. We get nor, we call it, which looks like this. And it means not or. So basically our or up there, it is not that. Then we get what's called NAND, which is basically not and. So it's the opposite of and. And then EOR is exclusive or. And we'll talk about what all that means in a minute. So let's do an example. So we'll do our P, Q tables again. True, remember, true, true, false, false. True, false, true, false. So we are going to do P, not, nor Q. And basically what this means is it's negate or. So what it's sometimes easier to do is you can look up at the or you can make a table here for the or. So let's start over here and we'll go P or Q. Remember, only one has to be true. So if they're both true, this is true. If one is true, it's true. One of the other is true, it's true. Both false, it's false. So that's P or Q. So then P nor Q, not or. It's just the opposite of this. If this is true, it's false. If this is true, it's false. If this is true, it's false. If this is false, it's true. So you're just negating that or. Same with the NAND. So we could come up here. Well, we'll just make another one. So I'm not writing here. We'll go P, Q. We'll go P and Q, P NAND Q. So not and. It's the negate of the and. Remember, we always start true, true, false, false. Alternating true, false, true, false. And the and, they both have to be true. So here they're both true. Nowhere else are they both true. So that's my and then we negate that. So whatever this is, it's the opposite. So that is my NAND. We negate the and. All right, last one is that exclusive or. Just want to go through that. The video is getting a little long, but we'll make sure we go through that. So EOR, which is like this, exclusive or, What does that mean? That means exactly one of P or Q must be true to be true. So if I've got my PQ table, true, true, false, false, true, false, true, false. It's not a negation of the or, so no need to look at the or beforehand. So exclusive or is just this, exactly one. So here both are true, not exactly one, so that is false. One is true, so it's true. Here Q is true, so it's true. And then both are false, so it's false, not exactly one. So that is an introduction to our beginning of our truth tables and our simple and compound connectors. We'll do some more complex ones in the lessons coming up.